Okay, welcome back. So yeah, I'm recording today, but on Wednesday I'll be back to um, live like normal. So anyway, so last time we had discussed what we did at the very end was discuss the orthogonal decomposition theorem, which basically is the souped up version of what we discussed before, where before we had discussed projecting a vector onto a one-dimensional subspace, right? And this was something you'd seen in Calc 3. The notion of projecting a vector onto another vector was really projecting a vector onto a line spanned by that vector. So it's projecting vector onto one-dimensional subspace spanned by that vector. But actually, we can generalize this process, and we can project that vector onto the subspace W, where W is just any subspace of Rn. We can similarly define this projection. So note that doing this in the case that W is dimension 1 would yield this first term, which is exactly the term that we had in what I called, I think, the nameless theorem. Right, was what I called it before. And so anyway, this was the method by which we did it. So whenever you see y hat here, that is the orthogonal projection. And so the motivation for wanting to do this in the first place is so that we could take a generic vector in Rn and write it as a vector sum y hat plus z, where y hat is in the subspace, right? And z is in the perpendicular complement, right? The orthogonal complement to the subspace. So y hat's in W and z's in W perp, right? And the idea, of course, is doing this in the case that y is not, is not in W. But you can think for a second about what you would do here in the event that y was in W, right? So what would you do here in the case that y was actually already in W? What is y hat in that case? Maybe I'll leave that open to your own investigations, right? You'll quickly figure out what it is that goes on here. And anyway, in this notation, y hat was called the orthogonal projection of y onto the subspace W. Okay, now W is spanned by this orthogonal basis U1 UP, and so that's why we can actually immediately write all these weights out in exactly this form. This is the orthogonal basis theorem, or orthogonal basis representation theorem. Okay, and so let's do one example of this, and then I'll move on to the next big named theorem. So I want to do an example of this. Remember, I drew a picture of this last time. So my picture looked like this. Again, the idea is that I have vector y. I have subspace W. Of course, here I've written it as a plane. Doesn't need to be. But in that case, my orthogonal projection of y onto W might look like this. In that case, the normal component, or the orthogonal component here, is z, and so y is y hat plus z in this way. So this is actually what I discussed at the end last time. Okay, so let's do an example of this. So let say u1 be the vector in R3 2, 5, minus 1. Let u2 be another vector in R3, which is minus 2, 1, 1. And let y be another vector in R3, which is just 1, 2, 3. Okay. So note that the set of vectors u1, u2 form an orthogonal basis for their span. All right, so note that these form an orthogonal basis for W, which is the span of those two vectors. Well, when you have two vectors, it's really easy to check that they're on orthogonal basis. Just dot them together, right? Those are the only distinct pairs you can make. 2 times minus 2 plus 5 times 1 plus minus 1 times 1, that's minus 5 plus 5, so that's 0. So yeah, this is an orthogonal basis for W. So I want to write y as a sum of a vector in W and another vector in W perp. Right? This was the original motivation, right? i.e., I'm going to be writing out this y hat plus z business, right? Okay. So let's do this following the orthogonal decomposition theorem. So y hat, really all I need to find is y hat because y is already given. If I can find y hat, I can find z immediately by just doing y minus y hat. Right, so all I need to do is find y hat. But by the orthogonal decomposition theorem, just flashing it on the screen for a second again. There it is. By the orthogonal decomposition theorem, we know exactly what y hat is. Okay, now here I only have u1 and u2, so there's only two terms in that orthogonal decomposition. So then to see what those two terms are, I'm just going to write this out fully. So y hat is y dotted with u1 over u1 dotted with itself. That's the scalar times u1 plus y dotted with u2 over u2 dotted with itself times u2. Right. So here's the orthogonal projection of y onto w. So now I just need to compute these things. I already have u1 and u2, so all I need to do is compute these four things real quick. So what is y dotted with u1? Well, y dotted with u1, this is 1 times 2 plus 2 times 5 plus 3 times minus 1. So 2 plus 10, that's 12 minus 3, so that's 9. Okay, what's u1 dotted with itself? So this is 4 plus 25 plus 1. All right, so that's 26 plus 4, that's 30. Okay, I need to compute numerator, denominator of this one too. So what's y dotted with u2? This is 1 times minus 2 plus 2 times 1 plus 3 times 1, so that's 3. And u2 dotted with itself. So this is 4 plus 1 plus 1, so that's 6. Okay, and so just writing this out, I'm not even going to simplify yet. So this is 9 over 30 times u1. u1 is the vector 2, 5, minus 1. Plus 3 over 6 times u2. u2 is the vector minus 2, 1, 1. Right. Okay. So I can simplify this just a little bit. So if I simplify this, so this is 3 times 3, this is 3 times 10, so this is 3/10, and this is 1/2. If I actually do this addition, let's see what do we get here. So apparently I get minus 2/5, 2 and 1/5. You can check that on your own. Okay, so I get a vector here. And this is my y hat. Okay, note also that y minus y hat, which is z, right? This is y minus y hat. So this is the vector y, which is 1, 2, 3, minus y hat, which is minus 2/5, 2 and 1/5. What is this? This is 7/5, 0, 14/5. Okay. All right. Now this theorem, the orthogonal decomposition theorem, automatically guarantees that this thing is in W perp, right? So this is in W, and this is in W. This is automatically in W. It's a linear combination of U1 and U2, so it's clearly in W. W is the span of those vectors. But this is actually guaranteed to be in W perp. You could check it if you wanted to. Dot these things together to see that this is actually true. So I would have I would have minus 14 over 25 plus 2 times 0, so that's 0, plus 14 over 25. That is indeed orthogonal to that vector, right? Now, of course, that doesn't really prove that it's in W perp. The proof of this comes from the proof of the theorem, which I didn't do. But the proof of the orthogonal decomposition theorem tells you why this works in this way. But the theorem guarantees that this is always in W perp. This is just a nice check, right? What I mean is that just because it's perpendicular to this vector doesn't mean it's perpendicular to every vector in W, but this is just a nice way to check, right? It should at least be perpendicular to that vector. Okay, and so, y is expressible as minus 2 fifths, 2 1/5, plus 7 fifths, 0, 14 fifths. Okay, where this vector is in W and this vector is in W perp. Right? Also, just check with yourself to make sure that this actually matches up with y. If I add these together, I get minus 2 fifths plus 7 fifths. That's 5 fifths. Here, let's just do it here. All right, so that's 5 fifths. This is 2, and this is 15 fifths. So this is 1, 2, 3. All right, so this is indeed y, and I've written y as a sum of a vector in W and in W perp. Okay, which was my original motivation for seeing if there was a theorem like this that was true or not anyway. Okay. Okay. All right. So now I want to return to the question I asked. I said that you could investigate it on your own, but I'm going to give you the answer now anyway. So what happens if y is actually in W? So let as usual, U1 to UP be an orthogonal basis for W. So let those be an orthogonal basis for W. What if y is in W? Well, what if that's the case, right? That could always happen. So just pick any vector in W, call it y. What is y hat? Well, if we actually look at this formula, then what do we get if y is actually in W? Well, what we get is that this formula is exactly the same as the formula in the nameless theorem. Okay, so here's the nameless theorem. Let me zoom in so that it's not all. So there's the nameless theorem. It's got smudges on it. That's okay. So if I have an orthogonal projection here, then y has weights, right? Written as linear combination of the U1 through UP, where the weights are given by this. But notice what this is saying. Like, if I replace each of these C sub j's with this, what formula do I get? Well, I get the formula in the orthogonal decomposition theorem. But in the orthogonal decomposition theorem, this is a formula for y hat. In my nameless theorem, this is a formula for what? This is a formula for y. Okay, so in the event that you have a vector that is already in W, y hat is equal to y. In this case, y hat is equal to y, i.e. the orthogonal projection of y onto W is just y. But intuitively, that is exactly what it should be, right? So if we go back to our picture, so looking at this picture, I've drawn it, of course, purposefully so that our vector y is not in W. But what if our vector y is just some vector lying here in W? Let me draw it with like a red pen. What if our y looks like this, right? What if this is our y? Well, then the orthogonal projection is just this very same vector, right? Here's y hat as well. Okay, there's nothing to project to. You don't need to project anywhere. You're already there, right? So that's the idea. That's what's going on. Okay. So let's do a quick example of, actually, yeah, I don't need to do an example. I'll just immediately go into what is meant here. So if y is already in W, then the projection of y onto W is just y. This is telling us a fact that is maybe tidying up one nice conceptual thing with a theorem I'm about to state. The theorem I'm about to state is called the best approximation theorem, and I will spoil the fun by already telling you that what it says is that if you have a vector y that is not in W, then conceptually what y hat is, we already know it's the orthogonal projection, and we already know that this allows us to write y as a sum of vectors, one that is in W and one that's perp to W, right? But conceptually, what's nice about the orthogonal projection is it is the closest vector to y that is in W. Okay, so then this makes sense why the orthogonal projection of y is itself when y is already in W, because in that case, the closest vector to y that is in W is itself, because it itself is in W. Okay, so I know that that sounds kind of like a mouthful, so I'll go ahead and state this theorem. So this one also has a name, and this is called the best approximation theorem. This has a lot of applications. If you take Math 401, which is kind of like more of the application side of linear algebra, you'll see many applications of the best approximation theorem. And so what does this say? So let W be a subspace of Rn. Let y be any vector in Rn. So let y just be a vector in Rn. Let y hat be the orthogonal projection of y onto W. Okay. Then, here's the important thing. Y hat is the closest point in W to y. Closest point or closest vector, right? Vectors are points and points are vectors. So y hat is the closest point in W to y. In the completely rigorous sense, in the sense that the distance from y to y hat is the minimum distance from y to any vector v among all vectors v and w, right? For all v in W distinct from y hat. Without that notion distinct from y hat, we could have had just a non-strict inequality here. Okay. All right. And so there's the best approximation theorem stated that this is another interpretation of my orthogonal projection, is that it is simply the closest, so y hat is the closest point in W to y. Okay. All right. And so let's do an example that reuses some of the numbers right, that we just did in our previous example. So let u1, u2, and y be as in the previous example. Okay, let's just flash those on the screen again. So that was my u1, u2, and y. Notice u1 and u2 form an orthogonal basis for w, which is the span of u1 and u2. So we had actually already computed y hat. So y hat was computed in this way. It was minus 2/5 to 1/5. We'll forget about z for a second. So recall, so then what is the closest, or maybe I should say by the best approximation theorem. Very apt name. So by the best approximation theorem, the closest point to y in W is y hat, which we found to be, let me remind myself, what do we find it to be? It's minus 2/5 2 and 1/5, right, which we computed in the previous example. Okay. Well, what is the distance? What is the distance from y to y hat? Note the distance from y to y hat is the length of the vector y minus, sorry, this is y minus y hat. So this is the length of the vector I get. Just to remind myself, y was 1, 2, 3. Okay. So this would be the length of this vector. So I'm not actually going to compute this length. You can if you want to. It's going to be some nasty configuration of numbers. But whatever that length is when you compute it, that's the smallest length among all any other vector you could have chosen in W is going to have a distance that is larger than this number. Okay. All right, so that's the key thing. Here's another fact, or maybe I'll write this as an example. We can define the distance from a vector to a subspace as the length of, alright, I mean, yes, you could define it as a length, but I'm going to say, I'm going to define it as the distance from, let's say, if I call my vector v, it's the distance from v to the closest point in my subspace, I'll say W, to the closest point in W to V, i.e. V hat. right, so we could define the distance from a vector to a subspace to be this. And so in that case, this distance would be this thing that I haven't computed here. Okay. So another thing that I could tell you is, so I could phrase the above question as, of course, in the above question, you didn't need to compute this actual distance, but from this, you can immediately compute it. So I can phrase the above question as compute the distance from Y to the subspace W, which is the span of those vectors, U1 and U2. All right, so this is another way I could have phrased that question. All right, as always in linear algebra courses, it's important to know all of the various ways that the same question can be phrased and rephrased. Okay. Okay, one more thing that I wanted to note that's nice that relates this to orthogonal matrices. And then I will get into the Gram-Schmidt process, and that will probably do it for the lecture. Okay. And so here's a theorem. This is just tidying up a bit. So if I have an orthonormal basis U1 to UP, so if this is an orthonormal basis, so this is an orthonormal basis for a subspace W of Rn, then the projection of Y onto W is Y dotted with U1 times U1 plus Y dotted with U2 times U2, and so on, plus Y dotted with UP, UP. Okay. This is, I mean, this is totally awesome, but actually it's really trivial to prove this fact. I'll bring that up here in a second. You already see how to do this, I'm sure. And then if we let U be the matrix that has these vectors Ui as columns, U1, U2, and so on, as columns, well, they form an orthonormal basis. So now U has orthonormal columns, so it's an orthogonal matrix. Well, if it's square, right? If it's not square, then it's just got orthogonal or orthonormal columns. Then the projection of Y onto W can also be thought of as U times U transpose Y, okay, for all Y in Rn. And so if the orthogonal basis is actually orthonormal, this way of writing Y, or the orthogonal projection of Y, onto W, is even nicer. This is obvious, right? Let's go back to our statement of the orthogonal decomposition theorem. Well, this is the orthogonal decomposition theorem where all these denominators are now 1. Right? Or all these denominators are 1 because this is an orthonormal basis, and so all of these vectors have length 1. If they have length 1, then their dot product with themselves is 1. So literally this is just the orthogonal decomposition theorem with an orthonormal rather than orthogonal basis. So all these denominators are 1. This leads to an extremely simple expression for Y hat, which also leads to this very nice way of writing Y hat as well, using an orthogonal matrix. Again, orthogonal in the case that you use a square matrix, but you can do this even if you use not square. Okay. So that's kind of the last thing I wanted to say about that. And now comes the important parts, probably one of the most important parts of Chapter 6, which is the Gram-Schmidt process. But before I actually get into what it is, what I'm going to say is big question. All right, so I know now, right, that orthogonal bases, this is the important part, right? Remember, yes, orthonormal bases are even better, but if you have an orthogonal basis, coming up with an orthonormal basis is trivial. You just scale every single vector by its length, which you can do if it's a non-zero vector. So, and that doesn't change the orthogonality because of the linearity of the dot product. Okay. So algebraic properties of dot product mean you can scale vectors without affecting it's not that you're not going to affect the dot product. It's that when the dot product is 0, you're not going to affect it, right? So scaling vectors in an orthogonal basis doesn't change their orthogonality. So all of the pairwise distinct dot products from all those vectors are still going to be 0. And so what this means is going from orthogonal to orthonormal is trivial. That's easy. So it's orthogonal that really is the thing. So we know now that orthogonal bases are great, right? Are extremely convenient, right? They allow these computations to be done very, very easily compared to a generic basis. The big question, though, is how do I construct an orthogonal basis for a vector space? And of course, we can just consider it as a subspace. So how can I construct an orthogonal, there's no D here, how can I construct an orthogonal basis for some subspace W of Rn given just a basis for W? That is just a generic basis for W. Here is the key question, right? So as someone pointed out previously, if you're in R3 and you have two vectors that are orthogonal, getting a third one that's orthogonal to both is really easy. You can just cross them. All right, so cross product does exactly that. But if you move to higher dimensions, right, if you try to do the same thing for R4, R5, and so on, then it's no longer something that you can really do. So how would I do this, right? How would I construct an orthogonal basis for a subspace in this way? Well, the answer is the Gram-Schmidt process. So the answer is the Gram-Schmidt process. Okay, so this is the subject of a subsection of Chapter 6 titled the Gram-Schmidt process. Okay, so what is the Gram-Schmidt process? Well, I'm going to list the process first, and then we're going to do an example. Textbook does it in the opposite order. It does the example to kind of motivate the process, but I'm just going to spill the process itself. So this is a theorem. This is the Gram-Schmidt process. But the entire purpose of the Gram-Schmidt process is starting out with a normal basis for some subspace of Rn and constructing an orthogonal basis, okay, for that. This is good enough to automatically construct an orthonormal basis if you want one by, like we said, scaling the length. Okay, so given a basis that is, so we'll call this x1 to, say, xp. So given a basis x1 to xp for a non-zero subspace W of Rn, define the following vectors. So define v1 is defined to be the vector x1. Okay. v2 is defined to be the vector x2, that's the second vector in this list, right, minus x sub 2 dotted with v1 divided by v1 dotted with itself times v1. Remember, v1 is just x1. Right? So v2's definition relies on v1's definition. Okay. All right. And so what is v sub 3? So v sub 3 is defined to be x sub 3 minus x sub 3 dotted with v1 over v1 dotted with itself times v1 minus x sub 3 dotted with v2 over v2 dotted with itself times v2. This process is continued until you get to Vp. V sub p is defined to be x sub p minus x sub p dotted with v1 over v1 dotted with itself times v1 minus x sub p dotted with v2 over v2 dotted with itself times v2. And this process is continued until I end with x sub p dotted with v sub p minus 1 over v sub p minus 1 dotted with itself times v sub p minus 1. All right, so I've defined p vectors using only the p vectors in my original basis. And it turns out that these p vectors are orthogonal. So then set v1 to vp is an orthogonal basis. So this is an orthogonal basis for W. Okay. Also, so even better, the span of the vectors v1 up to vk, this is actually the same thing as the span of the vectors x1 up to xk for all values of k between 1 and p. So what this is saying is you can even treat this in intermediate steps, right? So you could actually do this for subspaces of the subspace W similarly, right? So at each step, essentially these spans are the same. So this is a really nice fact. You can see just by looking at this, even if you didn't understand anything about what's going on, just knowing the algebraic formula for the projection, you can see that clearly this process is related to orthogonal projection, because this stuff that you're subtracting off from these vectors are exactly the terms that show up in an orthogonal projection, right? And so if you think carefully about this, the proof is actually not that long. It's only like one decently short paragraph at the top of page, well, in my edition it's page 358, but this is in chapter 6, section 4. So this is the proof of the Gram-Schmidt process here. So I think it is prudent to do like one good example that shows you really what's going on, and I think that will probably do it for this lecture. Okay, so you'll have plenty of chances to go over the Gram-Schmidt process tomorrow in discussion. Okay, so here's our big mega example of the Gram-Schmidt process. If you're confused, you can pause the video on this little bit here that shows the entire way that this is defined. Okay, so there's that. If you wanted to go back and have a look at that. But I'm going to be referring to that, and it's going to be off screen because I don't have room for it because it took up a whole page by itself. Okay, so let x sub 1, we'll say, be the vector 1, 1, 1, 1, 1, 1, 1, 1. And let x sub 2 be the vector, say, 0, 1, 1, 1. And x sub 3 be the vector 0, 0, 1, 1. Okay. Then this set of vectors is clearly linearly independent. So this is linearly independent. And so they form a basis for W, right? Some subspace. So if W is equal to the span of x sub 1, x sub 2, and x sub 3, then this set x sub 1, x sub 2, x sub 3 forms a basis for W of R4. It forms a basis for W, which is a subspace of R4. Okay. All right, so what we want to do is construct an orthogonal basis for W. You can clearly see just by checking, check any pair you want, you can see that they're not orthogonal, right? No, none of those dot products is 0. So construct an orthogonal basis for W, right? So this is a great example because here we're starting with a set that's, it's a basis that's maximally not orthogonal, if that's a thing. It is a basis where none of the pairwise distinct dot products are, none of those are 0, right? So none of these are orthogonal to one another, right? So we have nothing to start us off, basically. Okay, so I want to apply the Gram-Schmidt process. So we apply Gram-Schmidt, so GS. That's what I will abbreviate it as. Okay, so then what's step 1, right? So step 1 is I define my vector v1 to just be x1. I'm not even going to alter the order of these. So define v1 to be x1. Right, so v1 is x1. Yeah, that's easy enough. Okay, my subspace associated to this would be the span of, so the span of v1 and the span of x1 would be the same. That's trivial here because they're literally the same vector. Step 2, now I define v2, right, to be this. I'm going to write out the formula again. This is x sub 2 minus x sub 2 dotted with v1 over v1 dotted with itself times v1. But v1 and x1 are the same by step 1, right? And so I just need to compute some things. So x2 dotted with x2 dotted with v1, that's the same thing as x2 dotted with x1, and I can compute that here. So x2 dotted with x1, this is 1 plus 1 times 0 plus 1 times 1 plus 1 times 1 plus 1 times 1, so that's 3. Okay, so that's 3. Okay, and then v1 dotted with itself, well, that's just x1 dotted with itself, which is 1 squared plus 1 squared plus 1 squared plus 1 squared, so that's 4. And so what this really is the vector x2, which is 0, 1, 1, 1, minus 3/4 times the vector v1, which is x1, so that's 1, 1, 1, 1. And so what is this vector? Well, this is the vector 0 minus 3/4 times 1, so that's minus 3/4. This is 1 minus 3/4, so that's 1/4. This is 1 minus 3/4, so that's also 1/4. This is 1 minus 3/4, so that's again 1/4. Okay, so there's my V2, right? Here's V2 right there. Okay. Now, what do you notice about this vector? Well, this vector is shit, right? This vector is terrible. This vector's, I mean, okay, it's you know, they're rational numbers. It's not that bad. You know, they're not really, really bad numbers, but I mean, for computation's sake, doing this by hand, this is terrible. Okay, but here, trick, right? Trick time. Here is a trick that can be very handy when you're doing this by hand. What is the trick? You have a vector here that is given to you right here. Now, do you need to do this? No, this is totally optional. You don't have to do this. So if you continue the Gram-Schmidt process using this vector you got out of this process just like this, you would still get a perfectly fine answer. It'd be totally fine. The trick here is, remember, I said earlier that scaling a vector that is in an orthogonal basis doesn't affect the orthogonality. Okay. Now we use that to go from an orthogonal basis to an orthonormal basis, and the thing that we were scaling it by was 1 over its length. Okay. And so here, what we want to do now is not scale it by that particular scalar. I just scale it by whatever would make this thing nicer. The trick is I can define V2 prime to be, say, 4 times V2 that I found here. And what is this? This would be minus 3, 1, 1, 1. This is a nicer thing to deal with than the V2 that I originally got out. And this will still be orthogonal, right? So this will still be orthogonal to the rest. Okay. So that's why this is a very nice trick to know. This can save you a lot of time when it comes to, and just a lot of headache when it comes to doing these computations, right? So if you're doing this by hand in person, this would be one thing. Of course, you guys are doing all this, you know, online, and so you have access to any kind of means that you wanted to check. If you wanted to check your answers, you know, this is no matter how bad the algebra is, it doesn't really matter as much. But still, this is something that you should know how to do, because also conceptually, it is nice to understand. Like, oh yeah, it doesn't change the fundamental property of orthogonality if I scale one of those vectors. And so I have two vectors right now. I have v1, which is just x1, and I have this v2 prime, which is this thing. You could check at this stage if you really wanted to. So you could check that this v2 prime dotted with v1, which is x1, is actually orthogonal. So let's check real quick. 1 times minus 3 plus 1 times 1 plus 1 times 1 plus 1 times 1. That's minus 3 plus 3. That's 0, right? So this is 0, just to check, right? Okay. So that dot product, I was doing it off screen there. That dot product is 0. Okay. So we have one more to find. We're not totally done yet. So one more example continued. Okay, and so what is V3 going to be? Well, V3 is going to be X3 minus X3 dotted with V1 over V1 dotted with itself times V1 minus X3 dotted with V2 prime, our replacement vector, over V2 prime dotted with itself times V2 prime. All right. This is our slightly modified. This is our slightly modified Gram-Schmidt process. So x3 was, not going to bring the other page back. You can rewind the video. So this is 0, 0, 1, 1 here, minus x sub 3 dotted with v1 is over v1 dotted with, so this is 2 over 4 times v1, which is just x1, so this is 1, 1, 1, 1, minus x sub 3 dotted with v2 prime is also 2 over v2 prime dotted with itself. Recall v2 prime is minus 3, 1, 1, 1, so this is 9 plus 1 plus 1 plus 1, so 9 plus 3, so that's 12. This is 2 over 12 times v2 prime, which is minus 3, 1, 1, 1. Okay, and carrying out this entire process, this is, so what is this? Let's see. So this is 0 minus 1/2 minus 1/2. So that is just 0. And then next, this is 0 minus 1/2 minus 1/6. 1/2 is 3/6. So this is 0 minus 4/6. So it's minus 2/3, right? So yeah, this is minus 2/3. And then similarly, this is going to be 1 instead, so this is going to be 1/3 and 1/3 here. Let me give myself more room here. So this is 0 minus 2/3, 1/3, 1/3, right? Because these entries are the same, the only difference here is 1, so I just add 1 to this one. All right, there we go. Okay. So I could scale this again if I was going to continue, right? So if I was going to keep going, if I had a Gram-Schmidt process that was longer, I could scale this again by 3 if I wanted to, but I can actually stop here. So here's my v3. Thus, our set v1, v2 prime, if you like, you could also use v2, but yeah, v2 prime, if you like, and v3 is an orthogonal basis for W. And so you should check, if you don't believe, you should check that the dot product, those pairwise dot products for those 3 vectors are all 0, right? So check those and you will be made a believer that this actually works. Okay. So that's the Gram-Schmidt method, or the Gram-Schmidt process. So this is going to be our way of constructing orthogonal bases. So if you see a problem, and in that problem you need to construct an orthogonal basis, Gram-Schmidt is the answer to that. This is basically the only method you have of doing it, except in very, very simple cases. All right. So that's that. You have a discussion tomorrow where you're going to do a bunch of practice with Gram-Schmidt and other orthogonality related things. I have a couple more things I'm going to say about chapter 6 stuff. So I'm going to mention the QR factorization of matrix, and I'm going to mention some least squares problems, which might take me a whole lecture if I really, really wanted to get into the conceptual stuff. But after that, we'll be moving on to chapter 7. That will pretty much do it for chapter 6. We'll be moving on to chapter 7, symmetric matrices, and some really fun stuff. So anyway, that is the plan. So I will see you all on Wednesday. I'll be doing live lecture on Wednesday. I will also have some office hours later in the week. I'll let you know when they're going to be. They won't be sooner than Friday, but on Friday I may have them next Monday instead of this week. So we'll see. Anyway, and I think I mentioned your exam is going to be due, or is going to be posted, I think, on Friday, and then it'll be due on Wednesday, something like that, or I don't know. Yeah, it'll roughly like that. You'll have plenty of time to do it. So anyway, I will see you all soon.